Good morning, ladies and gentlemen. This is the fourth week of our academic semester. This is emergency solution because, as you can see, the room is empty, and I have to provide you the seminar number 4. So I will try to solve everything for you and send you a link with this video record. So, if you remember, on the last seminar number 3, we finished this small example about the contingency table. We started with descriptive analysis of dependence, and I said to you that today we will continue. We will continue with a little bit larger contingency table with 3 rows and 2 columns. So, there is example, there was observed the relation between the level of alcohol in blood, low, middle and high, and the speed of the reaction in a car during driving. In most of the countries in the world, there is prohibited to drive with alcohol in blood. If you're drinking, you're not allowed to drive automobile. So we would like to calculate if there is a relation, yeah, the dependence between the speed of reaction in car and the level of alcohol in blood. So if you remember, on last seminar, we established frequencies, absolute frequencies N, E, J, observed frequencies, empirical frequencies, yes? Level of alcohol, we have here low, middle and high level, and speed of reaction good and bad. So I will draw for you the table on whiteboard. So please wait a second. Okay, 6 positions, yes? Good. 53, bad, 12, 5 and 15, 2 and 13. Okay, so on the whiteboard we have empirical frequencies, observed frequencies, N, E, J. We'll open formulas. There is a chapter, descriptive analysis of dependence, contingency table, rows and columns. We have 3 rows, 2 columns. So we have to create another table with expected frequencies, independent frequencies, NEJ with stripe. So there will be NEJ with stripe again. Good reaction, bad reaction, low, middle and high. Okay, so the same table will be here, and you know that we need to calculate marginal frequencies. Marginal frequencies, NE dot and N dot J, side frequencies, frequencies on the side of the table. So NE dot and N dot J. Okay, what is it? Marginal frequency. 53 and 12. Yes, 53 plus 12 will be here. 53 plus 12 result is 65. 5 plus 15. 5 plus 15 is 20. Yes. And the last marginal frequency here, 2 plus 13, 2 plus 13 is 15. Okay, so we have here marginal frequencies, 65, 20, 15, and another marginal frequency is 53, plus 5, plus 2, 60. Yeah, so there we have 60, and 12, plus 15, plus 13, 40. Okay, so we have a table with marginal frequencies. 60 plus 40 is 100. 100 drivers, so there is n sample size, yes? We have 100 drivers. 65 plus 20 plus 15 is 100, yes? The sum of rows must be equal to the sum of columns. Okay, marginal frequencies. And now, NEJ with stripe. We will recalculate this table, empirical table, to another table, expected table, table with expected frequencies. So, NEJ with stripe is equal to NE dot times N dot J divided by N. Yes, so we need to calculate 6 new values. Okay, so I will write the steps here. After I will delete it and I will write the results. Yes, because what would be here? 65 times 60. Yes, 65 times 60 divided by 100 drivers. 65 times 40 divided by 100 drivers. Yes, in numerator there is a multiplication of marginal frequencies, the side frequencies. 20 and 60. 20 times 60 divided by 100. 20 times 40 divided by 100. 15 times 60 divided by 100. And 15 times 40 divided by 100. Okay, so now the first value, 65 times 60 divided by 100, 39. Okay, so I will delete these values and there will be a result 39. 39. 65 times 40 divided by 100. 26. 20 and 60. 20 times 60 divided by 100, 12. 20 times 40. 20 times 40 divided by 100, 8. 15 and 60. 15 times 60 divided by 100, 9. And the final value, 15 times 40 divided by 106. Okay, so this is table with expected frequencies, yes, theoretical frequencies. Okay, and now for the calculation of measures of existing dependence, Pearson coefficient C and Kramer coefficient V, we need to calculate statistic G. Yes, G value. G value is summation through all rows, summation through all columns from squared differences NEJ, NEJ with stripe, and this is divided by NEJ with stripe. So 6 squared differences NEJ, NEJ with stripe. This is in squares, yes, and this is divided by NEJ with stripe. Okay, I will start here on the left side on the whiteboard. So this value 53, 53 minus this value 39, 39. This is in squares divided by 39 plus 5 other values, yes, 5 other squared differences divided by expected theoretical frequency, 12 and 26. 12 minus 26 squared divided by 26, and we can continue plus. I will delete this formula because you have opened formulas in front of you. So we can check it. 5 and 12. 5 minus 12 squared divided by 12 plus 15 and 8. 15 minus 8 squared divided by 8 plus 2 and 9. 2 minus 9 squared divided by 9 plus 13 and 6. 13 minus 6 squared divided by 6. 1, 2, 3, 4, 5, 6 values, yes? So 53 minus 39 squared divided by 39. I will use only 2 decimals, yes? It will be enough. 5.03. 5.03 plus 12 minus 26 squared divided by 26. 7.54. 7.54 plus 5 minus 12 squared divided by 12. 4.08. 4.08 plus 15 and 8. 15 minus 8 squared divided by 8. 6.13. 6.13 plus 1, 2, 3, 4. Fifth value 2 minus 9 squared divided by 9. 5.44 plus last value 13 minus 6 squared divided by 6. 8.17. 8.17. The summation of these 6 values is statistic G. Yes, we need this statistic for calculation of Pearson and Kramer coefficient of contingency. 5.03 plus 7.54 plus 4.08 plus 6.13 plus 5.44 plus 8.17. 36.39. I think that it's not necessary to have here this table, and the result G, statistic G, is equal to 36.39. Okay, so it's G statistic. Okay. And now we have statistic G, there is a C value and V value. So Pearson's coefficient C is equal to, there is a square root. In numerator we have statistic G, 36.39 divided by, in denominator G plus N, sample size, our 100 drivers, yes, 36.39 plus 100. Okay, I will delete the rest of the whiteboard because we need more space. Okay, so please wait a second. Because it's necessary also interpret the result. Yes, we can calculate Pearson C, but we must know what is the result. So 36.39 divided by 100. 36.39. 136.39 square root. Okay, result 0.5165. 5165. Okay. On the last seminar, we talked about this coefficient, Pearson C. You remember that this coefficient has unknown maximum value. We must calculate this maximum. Minimum is 0, yes? If there is no dependence between the level of alcohol in blood and the speed of direction in car, result will be 0 of this coefficient, yes? but we must calculate maximum. Maximum is square root from maximum of this coefficient is square root from m. What is m? M is minimum from rows and columns. We have 3 rows, 2 columns. What is smaller, 2 or 3? 2 is smaller, yes? So there is 2 minus 1 in parentheses, 2 minus 1 divided by m. Minimum from rows and columns, yes? 2. Smaller is 2. So this is the maximum, the potential maximum of Pearson coefficient C. So 2 minus 1 is 1. 1 divided by 2 divided by 2 square root from this value. 2 minus 1 is 1 divided by 2 and square root from this value 0.707. So minimum is 0, maximum is 0.707. Our calculated value is 0.51. Yes, it's quite close to 0.707. So there is strong dependence between the level of alcohol in blood and the speed of the reaction. But you know from presentation of Mr. Hellman that this evaluation is subjective. Yes, this interpretation, verbal interpretation is subjective. Strong dependence, yes, probably strong dependence. But we can calculate Kramer's V, Kramer coefficient, Kramer's V, and this Kramer coefficient has maximum 1. So according to my opinion, this is better coefficient. There is square root in nominator, statistic G, 36.39 divided by n, sample size 100 times, and in parentheses we have n minus 1, minimum from rows and columns, so 2 minus 1. Yes, 2 is smaller than 3. Okay, so there is 36.39 divided by 100. 100. Square root from this value 0.603. Okay, and we know that this coefficient is element of range 0 and 1. Okay, yes, 0.6. You know that minimum is 0, maximum is 1, and we are at the position 0.6. Yes. Middle strong dependence, yes, evaluation, interpretation is subjective, but we know that we are on this position 0.6, yes, we are able to imagine the strength of existing dependence, yes, so probably yes, there is dependence between the level of alcohol in blood and the speed of the reaction in car. This was contingency table. In the same presentation, where you have a topic about contingency table, you have also analysis of variance method, Anova, one-way Anova. We will start with descriptive part, about Anova. There we can analyze more factors and the influence of this factor on our observation. We have here observed points, number of points from the final test, and the factor is the teacher who teach these students. We observed 12 students, how many points they got from the final test. So we have your values. This is variable with values from 0 to 60. And we know that 4 from the students were always attended the classes of one of 3 teachers, Mr. McDonald, Mr. King, and Mr. Vance. And there is a question, does the person of the teacher the influence on the number of achieved points from the final test? This is analysis of variance Anova one-way Anova method. We must calculate 2 types of variance. Do you remember the composition of variance to groups? Within group variability and between group variability. So we will do this one more time, and we'll use this decomposition here in this type of example. So I will open formulas, and you see there you have Pearson coefficient C, Kramer V, and below we have analysis of variance. We know that total sum of squares, yes, SS, it means sum of squares total is equal to sum of squares can be decomposed to TR. Mr. Hellman using word treatment, but you can also use theoretical, yes, treatment or theoretical or explained sum of squares and error sum of squares. So STR, sum of squares total is equal to S sum of squares SS TR, treatment, theoretical, and error sum of squares. We'll start with calculation of treatment sum of squares. We need to know data, the data set. Mr. Hellman using indices J. So XJE in this order, XJE. I will rewrite the data on the whiteboard, yes? So teacher number 1, yes, Mr. McDonald. Teacher number 1 and number of points. 53, 47, 55, and 50. So this is the first group, yes, the first teacher. Second teacher, Mr. King. Number 2. Okay, values 42, 48, 48, 50. And the last, third teacher, Mr. Vance. Number 3. Teacher number 3. 39, 46, 39, and 43. Okay. So 3 groups, 3 teachers, and we will start with calculation of treatment sum of squares, STR, theoretical sum of squares. What we need a total mean and individual means for the particular teacher. So XJ with stripe, yes, and the total mean will be calculated, for example, on the right side of the whiteboard. So what does it total mean? Total mean is a summation of 12 values divided by 12. Yes, the total mean, X with stripe. Okay, so 53 plus 47 plus 55 plus 50 plus 42 plus 48 plus 48 plus 50 plus 39 plus 46 plus 39 plus 43. Nominator 560, denominator 12. So result divided by 12, 46.67. 46.67 This is the total mean. And now, individual means. The means for a particular teacher, yes? Mr. McDonald. Summation of 4 values, yes? 53 plus 47 plus 55 plus 50. 205 divided by 4. Divided by 4. 51.25. 51.25. So this is the first mean, the mean for Mr. McDonald. 42 plus 48 plus 48 plus 50. 188 divided by 4 students, yes? Divided by 4. 47. 47. 39 plus 46 plus 39 plus 43. 167. 167 divided by 4. Divided by 4. 41.75. 41.75. Okay, we have here 3 individual means. The mean for Mr. McDonald, Mr. Pence, and Mr. King. Treatment sum of squares. In our formulas, we have sum of square differences between individual means and the total mean weighted by frequencies. Yes. So what is it? There is summation through all j, xj mean minus x with stripe. This is squared times mj. Okay. I will delete these partial results and this top part of the whiteboard. There is a total mean, yes? So, xj with stripe minus total mean squared weighted by nj. What is here? 51.25 minus 46.67 squared weighted by 4 students. And we can continue. So I will delete this part. I will write the total mean here, yes? X with stripe is equal to 46.67. Okay, 47 minus 46.67 squared weighted by 4 students. 41.75 minus 46.67 squared weighted by 4 students. 3 parts, 3 partial results, yes? 51.25 minus 46.67 squared times 4. 83.9. 83.9. 47 minus 46.67 squared times 4. 0.44. 0.44. 41.75 minus 46.67 squared times 4. 96.8. 96.8. Okay, the sum of these 3 values will be theoretical or treatment sum of squares, SSTR. Yes, theoretical or treatment sum of squares. 83.9 plus 0.44 plus 96.8. 181.14. 181.14. So this is first important sum of squares for our analysis. Yes. Okay. If you check formulas, you can see that treatment sum of squares, yes, using only one summation with all j's, yes. And now we can calculate, for example, total sum of squares, because for calculation of effect size, the statistic, the coefficient of existing dependence, we must know treatment sum of squares and the total sum of squares. Yeah? So we will continue with total sum of squares, but total sum of squares using two sums. Sum through all j, sum through all e. Yes? So all values xje minus the total mean. Okay, so we can do it. I will delete this part. Okay, and here on the top of the whiteboard there will be summation through all j, summation through all e, in parentheses squared differences between xje and the total mean. So xje, there is total mean squared. That's all, yes? So all values, there will be 53 minus total mean, 46.67. 46.67 squared. 47 minus 46.67 squared. 55 minus 46.67 squared. 50 minus 46.67 squared. And we can continue with the same mean. Yes, the total mean. Total sum of squares. Total mean, one mean. 42 minus 46.67 squared. 48 minus 46.67 squared. 48 minus 46.67 squared. 50 minus 46.67 squared. And we can continue. 39 minus 46.67 squared. 46 minus 46.67 squared. 39 minus 46.67 squared, and 43 minus 46.67 squared. Okay, 12 values, a lot of work, yes? You can use Excel if you want, you are at home, you have your notebook, your computer, you can use Excel. There is a constant, yes, the constant mean, so you can copy formulas. 53 minus 46.67 squared. 40.07. 40.07. 47 minus 46.67 squared. 0.11. 55. 55 minus 46.67 squared. 69.39. 69.39. 50. 50 minus 46.67 squared. 11.09. 11.09. 42. 42 minus 46.67 squared. 21.81. 21.81. 48. 48 minus 46.67 squared. 1.77. 1.77. Again 48. 1.77. 50. We already had 50 here. 11.09. 11.09. 39. 39 minus 46.67 squared. 58.83. 58.83. 46. 46 minus 46.67 squared. 0.45. 0.45. 39 again. 58.83. And last value 43 minus 46.67 squared. 13.47. 13.47. Okay, the sum of these 12 values should be total sum of squares. SS, sum of squares, total. Yes, total sum of squares. So 40.07 plus 0.11 plus 69.39 plus 11.09 plus 21.81 plus 1.77 plus 1.77 plus 11.09 plus 58.83 plus 0.45 plus 58.83 plus 13.47. 288.68 288.68. So this result is total sum of squares. Okay, I will delete these two columns because we don't need these partial steps anymore. And we know that total sum of squares is a summation of treatment, theoretical sum of squares, and error sum of squares. So this is a bonus for you, yes? You don't need to solve this for calculation of effect size, yes? We have everything. We have treatment and total sum of squares, but for practical purposes, we know that error sum of squares can be calculated like total sum of squares minus treatment, theoretical sum of squares, yes? So if you calculate 288.68 minus 181.14, you will obtain error sum of squares 288.68 minus 181.14, 107.54. Yes, this is sum of squares error. Yes, error sum of squares 107.54, and I will calculate for you the proof that we have correctly calculated results. Yes, I will calculate here error sum of squares, and we will see that the result will be around 107. I will make small mistakes in decimals, for example. Yes, error sum of squares. Sum through all j, sum through all e. Sum through all j, sum through all e, difference xje, and individual means. The means for the particular feature, yes? So there will be summation and summation. Sum through all j, sum through all e. xje minus xj with stripe squared, yes? Okay, that's all. So we must remember that it's necessary to change the mean, yes? In all group, the particular mean for a particular group. So 53 minus 51.25 squared. 47 minus 51.25 squared. 55 minus 51.25 squared. and 50 minus 51.25 squared. And now we must change the mean. Yes, we will change the mean. 42 minus 47 squared. 48 minus 47 squared. 48 minus 47 squared, and 50 minus 47 squared. Okay. And final mean, last mean for Mr. McDonald and King, Mr. King, yes. 39 minus 41.75 squared. 46 minus 41.75 squared. 39 minus 41.75 squared, and 43 minus 41.75 squared. Yes, we must change the mean. Yes, if you are changing the particular group, we must change the mean. Okay, so again, 12 partial results. 53 minus 51.25 squared. 3.06. 3.06. 47 minus 51.25 squared. 18.06. 18.06. 55 minus 51.25 squared. 14.06. 50 minus 51.25 squared. 1.56. 1.56. Okay. 5 squared 25. 1 squared is 1. 3 squared 9. Yes, so this was easy. This is easy. 39. 39 minus 41.75 squared. 7.56. 7.56. 46 minus 41.75 squared. 18.06. 18.06. 39 minus 41.75 squared. 7.56. Okay, this is the same result. 7.56 and 43. 43 minus 41.75 squared. 1.56. 1.56. Okay, again, 12 values. Yes. 3.06 plus 18.06 plus 14.06 plus 1.56 plus 27 plus 9 plus 7.56 plus 18.06 plus 7.56 plus 1.56. 107.48. Yes, you can see very small mistake in decimals, as because I used only 2 decimal positions, but it's all right. Yes, we have correct results. Okay, so I will return to this example. So we observed 12 students. How many points they got from the final test? 4 from these students were always attended the classes of one of 3 teachers, Mr. McDonald, King, and Benz. And there is a question: is the person of the teacher influence on the number of achieved points from the final test? We can calculate effect size. In other literature, you can find synonyms. For example, index of determination. Yes, index of determination, determination of the factor of the teacher. Yes, the power of this influence. Yes, we would like to interpret the power of this influence of the teacher on the number of achieved points. So, effect size, yes, is equal to treatment sum of squares divided by total sum of squares. Effect size, treatment sum of squares, 181.14 divided by total sum of squares, 288.68. 181.14 divided by 288.68. 0.627. 627. Okay. You know that if there will be perfect, strong dependence, strong influence, very strong, perfect influence of the teacher on the number of achieved points, this effect size will be equal to 1, because treatment theoretical sum of squares will be the same like total sum of squares. Yes, nominator. Yes, if the nominator is the same like denominator, result will be 1, and there will be strong, perfect, strong influence. So we know that this effect size is from range 0 and 1. Yes, so we know that this is element of range 0 and 1. Result 0.627. Again, you are able to interpret. The result in a sentence, yes, but you know that evaluation is subjective, yes. According to presentation of Mr. Hellman, you know that middle strong dependence, middle strong influence, it's my opinion, it's my subjective evaluation of this result, yes. So there is influence. I think that there is influence of the teacher on the number of achieved points. Okay, another example, 4.2. We'll continue with Anova method. Using the experiment, there was tested consumption of petrol, yes, using 3 types of petrol. There were done 5 experiments with each petrol. So it will be good to denote that we have again number of factors. Yes, we have 3 types of petrol. For example, Shell, OMV, and Ajib. Yes, we have 3 types of petrol from 3 petrol stations. So number of factors is equal to 3. There were done 5 experiments with each petrol. So 5 times 3 is equal to 15. We have 15 observations in total, yes. In the previous example, we analyzed 12 students. Now we are analyzing 15 observation of consumption of petrol, yes. Fill in the Anova table and try to decide in descriptive way whether the consumption depends on the type of petrol. It means measure the tightness of potential dependence. So we have here Anova table. In your presentation given by Mr. Hellman, you could read this Anova table. You know that in this Anova table we have 3 sum of squares. Yes. In previous example we talked about the total sum of squares. about the treatment sum of squares and about the error sum of squares. If you calculate this Anova, one-way Anova method in Excel, you will see the table where will be written between group variability, within group variability, and the total variability. Sum of squares is the same. So we have here the row total, and we know that total in column sum of squares, it means total sum of squares. Sum of squares total is equal to 0.2507, 0.250773. Okay, what else? There is another value on the second position, within group variability. Within group variability is error variability, and here in the column of sum of squares we can find, therefore we can find here error sum of squares. So error sum of squares error is equal to 0.080, 280. Okay, between group variability, in some software you can find synonyms: model variability, theoretical variability, explained variability. Yes, and in our terminology, in your formulas, you can find a treatment variability. In this situation, treatment sum of squares. Okay, treatment. So sum of squares, TR. We will calculate this treatment sum of squares like total sum of squares minus error sum of squares. Yes, difference, simple difference. So 0.250773 minus 0.080280. This is equal to 0.170493. Yes, treatment sum of squares. Okay, in this table we could continue with degrees of freedom, mean square, Fisher statistic, but you know from the presentation of Mr. Hellman that with mathematical statistics and hypothesis testing we will continue later. Yeah, so there you have written week 11. So you must wait. This is enough for us. We know sum of squares. We are able to calculate effect size. Effect size is equal to treatment sum of squares TR divided by sum of squares total. Yes, in our situation 0.170493 divided by 0.250773 divided by 0.250773. Okay, 0.6799. 6799. Okay, we know that this statistic is element of range from 0 to 1. So again, we are able to interpret as the strength of the dependence, of existing dependence. So probably there is dependence, yes? Middle strong dependence, because this result is 0.68. Yes, we know that maximum is 1, 0.68 is close to 1, there is strong dependence, middle strong dependence. So yes, there is dependence. On the consumption. Yes, if you use different type of petrol, there is a difference in the consumption. So we decided in the descriptive way that the consumption depends on the type of petrol. We calculated the tightness of dependence in effect size. Okay, dependence, characterizing of dependence. We are still in the descriptive, in the topics of descriptive way of existing dependence. I will continue. We are able to calculate the statistic, the measure of linear dependence between two variables. Yes, variable 1, variable 2, two different numerical variables. We have here boys, 15 boys, yes, and we observed two variables. These boys, basic school, for example, try to do squats and push-ups in the gym. Yes, and 15 boys at elementary school. There was measured how many of push-ups and squats they are able to do. We can expect that if the boy is strong, he is able to do a lot of squats and a lot of push-ups. Yes. If the boy is weak, he is not able to do a lot of squats and a lot of push-ups. So we can expect that there is mutual dependence, linear dependence between these two variables, and we are able to calculate, calculate this dependence by appropriate coefficient. We have a correlation coefficient in our formulas. Correlation coefficient is a statistic, yes, statistic from range -1 + 1, and we are able to measure the strength of this dependence. We have here these values. Maybe I will write these values on the whiteboard. So variable, we will check formulas. Correlation analysis. Variable x and variable y. Yes, we need to know only these two variables. So variable x and variable y. Data 1320. 5614. 356. 211. 2118. Yes. Maybe I will do these calculations in Excel because it will spend a lot of time. So there will be variable x, there will be variable y. We need at least 3 more columns. Variable x squared, variable y squared, and variable x times y. Yes, 3 new columns. Why? Because in formulas you can see we need to calculate means. The mean from variable x, the mean from variable y, the mean from multiplication x times y, and second power here x squared mean and y squared mean. Yes, so the means x with stripe, y with stripe, x squared stripe y squared stripe and x y square stripe. Yes, x y stripe. 1, 2, 3, 4, 5. 5 means. So I will use Excel. So please wait a second. I will screen. Excel is here. Number of squats, number of push-ups. Variable x, variable y. We will use, for example, 2 decimals. Yes. Okay. Can you see this screen? Okay. So there will be variable x and there will be variable y. Variable y. Okay, x and y. I will zoom this document, and now we need x squared. X squared. Center. Right button, format cells, superscript, okay. So second power of variable x and second power of variable y. Okay, so equal sign, this value, power function powered by 2, yes. Okay, so we have here second powers, yes. Variable y equal sign, this variable, yes, number of push-ups, powered by 2, second power of second variable, okay, powered by 2. Center, okay, and finally x, y, yes, multiplication, variable x and variable y, equal sign, number of squats, times number of push-ups. Okay. And now means, yes, I will use view, freeze panes. Okay. Yes, you can see there is row 42 with labels. I have here labels. Here labels and means. Here I will calculate means. Equal sign average. Average returns the average, the mean of its arguments. Average from these values, 15 values, yes? Average from 15 values, average for variable x. 3.20. 3.20. Average for variable y, 23.07. Average for variable x squared, 16.08. Average for variable y squared, 833.07. And average for variable x times y, 113.05. Okay, we will use the whiteboard, yes, one more time. So please wait a second. We will open formulas and we will calculate the correlation coefficient. Correlation coefficient Ryx. Denominator xy stripe, xy stripe minus x with stripe times y with stripe. This is divided by, there is square root, and we have here x squared mean minus x with stripe squared times y squared mean minus y mean squared. Okay, we know all values, yes? All values we have calculated here. So, in the denominator, 113.05 minus x 3.2 times y 23.07, and this is divided by, there is square root and x squared mean 16.08 minus mean 3.2 squared times second power of variable y 833.07 minus 23.07 squared. Okay, I will use the calculator. Numerator 113.05 minus 3.2 times 23.07. 39.226. Denominator, in denominator we have 16.08 minus 3.2 squared, 5.84. There is 833 minus 833.07 minus 23.07 squared, 300.8451 okay, times 5.84 square root from this value 41.916. Okay, this ratio is correlation coefficient. If you check the formulas, you can see that in numerator there is covariance. There is a covariance in numerator. Yes, numerator can be positive or negative, but denominator, yes, denominator is non-negative value. Non-negative value every time. Yes. Okay, if we check the formula for the correlation analysis, correlation coefficient, we can see numerator, denominator here. We calculated this ratio 39.226 and 41.916. Result is 0.9358. So this is correlation coefficient. We know that correlation coefficient, I will delete this formula. Correlation coefficient is statistic from range -1 + 1. Yes, R, X, Y is element of range from a -1 + 1. If the statistic, if this coefficient is close to -1, there is negative, strong negative dependence between variable x and variable y. If this coefficient is close to +1, there is a strong positive dependence between variable x and variable y. You can see this coefficient is very close to +1, so there is strong positive dependence between number of squats and number of push-ups in the gym. Yes. So there was a question. Wait a second. I will use view, freeze paints, unfreeze. Okay. So this example, 15 points at the elementary school. Calculate whether there is mutual linear dependence between the number of push-ups and number of squats by appropriate coefficient. Yes, there is strong positive dependence. If the boy is strong, he's able to do a lot of squats and a lot of push-ups. Yes, if the boy is weak, he is not able to do a lot of squats and a lot of push-ups. Okay, so correlation between two numerical variables. Okay. Okay, last example for today. In the previous example, we tried to calculate the statistic of dependence, yes, the characterization of dependence between variable 1 and variable 2. Now, we received the data from 6 households about the number of members in the household and their monthly expenditures in thousands Norwegian crowns. Yes, so we have here two variables, variable x and variable y. Yes, variable x, number of members in the household. 1 member, 2 members, 3, 4, 5, and 6. Yes, and monthly expenditures in thousands Norwegian crowns. 6, 8, 12, 6, 8, 12, 15, 22, and 23. Okay. We would like to calculate the correlation coefficient. And we would like to try to interpret the tightness of existing dependence. Why? You can imagine the chart. Yes, Mr. Hellman drew for you a chart in his presentation. There is variable x and there is variable y. Yes, 0 persons in the household, 1 person, 2 persons, 3, 4, 5, and 6 persons. Yes, and you can observe in this chart. Yes, you can observe the data. Yes, you can observe the data. This is only descriptive part of regression analysis. So you can observe if you have more persons in the house. Yes, more persons in the household. You need more money. You need more money for food, living costs, etc. So more larger monthly expenditures. Yes, more money is necessary if you have more persons in your house, in the household. So we would like to describe this dependence between number of members in the house and monthly expenditures. And we would like to calculate the correlation coefficient. Yes, in the same way like before. If you check your formulas, you can see that we need to calculate second power of variable x, second power of variable y, and mutual multiplication. Yes, x squared, y squared, and x y. X squared 1, 4, 9, 16, 25, and 36. Variable y 6 squared. 6 squared, 36. 8 squared is 64. 12 squared, 144. 15 squared, 225, 22 squared, 484, 23 squared, 529, 529, okay? So this column, this column, this column, and this column. 1 times 6 is 6. 2 times 8 is 16, 3 times 12, 36, 4 times 15, 60, 5 times 22, 110, and 6 times 23, 138, 138, okay, the means, yes, the means. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. 3.5, yes. 3.5. So there is the first mean. 6 plus 8 plus 12 plus 15 plus 22 plus 23 divided by 6. 14.73. 14.73. Second mean, yes? 1 plus 4 plus 9 plus 16 plus 25 plus 36 divided by 6. 15.17. 15.17. 36 plus 64 plus 144 plus 225 plus 484 plus 529 divided by 6, 247. And 6 plus 16 plus 36 plus 60 plus 110 plus 138 divided by 6, 61. Okay, so that's all, and now we can calculate correlation coefficient R, X, Y, yes? Correlation between number of persons in the household and monthly expenditures. In the numerator, 61 minus 3.5 times 14.73 divided by second square root, and there is second power of x, 15.17 minus 3.5 squared times, and there is y squared, 247 minus 14.33 squared. Okay, so here 15.17 minus 3.5 squared times 247 minus 14.33 squared. Square root from this value, and numerator 61 minus 3.5 times 14.33 divided by this value. Okay, correlation coefficient R, X, Y is equal to 0.9834. 9834. So there is very strong positive correlation. Yes, very strong positive correlation between number of members in the household and monthly expenditures. Yes, monthly expenditures in thousands Norwegian crowns. We will continue we are able to estimate the parameters of this function. This is a linear function, and we are able to calculate and estimate the parameters of this regression line. It is describing the dependence of the monthly expenditures on the number of members in the household. And we are able to interpret the value of the regression coefficient. So we need to estimate intercept and the slope of the regression line. What is necessary for calculation of intercept and slope of the regression line? Regression line, in our formulas, we have written regression line y is equal to b0 plus b1 x. Intercept and slope, yes? Intercept and slope of the regression line. Two coefficients to b. Firstly, we can calculate b1, the slope of the regression line, yes? b1, according to your formulas, b1 is calculated like, in a numerator, do you remember this numerator? X, y mean minus x mean times y mean. This is the same numerator like we have in the correlation coefficient, yes? So this is the same numerator divided by, and in denominator there is variance. Variance, x squared mean minus mean squared. We know everything is already calculated, yes? So we can take the values from this table. 61 minus 3.5 times 14.33. Yes, and this is divided by x squared mean 15.17 minus mean 3.5 squared. Yes, and the result is slope of the regression line. So nominator 61 minus 3.5 times 14.33 divided by denominator 15.17 minus 3.5 squared. 3.714. 3.714. So this is slope of the regression line. Slope of the regression line. Okay, and we can continue. We can continue with intercept B0. So again, we know everything for the calculation. Yes. I will delete. No, it's not necessary to delete anything. I will write it here. B0 is equal to mean from variable y 14.73 minus B1, this coefficient slope 3.714 times x mean 3.5. So this will be intercept 14.33 minus 3.714 times 3.5. 1.331. So this is intercept. This is intercept of the regression line. This is slope of the regression line, and now we are able to write. The formula of the regression line. Yes, y is equal to intercept 1.331 plus 3.714 times x. So this is equation of the regression line, describing the dependence of monthly expenditures and the number of members in the household, and we are able to interpret the value of the regression coefficient. We are able to interpret the value of two regression coefficients. Yes, I will delete these two columns. And do you remember this chart? Yes. This chart, and there is regression line. Yes. Imagine that variable x is equal to 0. There is nobody in the house. Yes. Household is empty, so 0 persons. And there is variable y, there is variable x. 0 persons in the house. Yes. There is value 1.331. Intercept. Yes, what is it? 1,331 Norwegian crowns. Even if the house is empty, yes, you must pay, for example, internet connection, some permanent payments. Yes, so even if the house is empty, this is some autonomous expenditure, yes, which must be paid even if there is nobody home, yes. And with every other person, yes, there is average increasing of expenditures by 3,714 Norwegian crowns. Yes. One more person in the house, you need more money. Yes, for monthly expenditures, more by 3,714. So this is average increasing with every other person in the household. Yes. So some autonomous consumption, autonomous expenditure, which must be paid even if the house is empty, and average increasing of expenditures with every other person. Using this model, we are able to do estimates. Yes, we have model, and we are able to calculate estimate. For example, estimate if we have 4 members in the house. Yes, using regression model, estimate the average expenditures of the household with 4 members. So variable y is equal to 1.331 plus 3.714 times 4 members. Yes. 1.331 plus 3.714 times 4 members. 16.187. What it means? 16,187 Norwegian crowns. We have a data, yes? That is data set. And you can see, according to data, 4 members needed 15,000 Norwegian crowns. So there is a difference. 16,000, 15,000. Is this difference large or not? Correlation coefficient is strong, yes? So probably it's not significant difference, but we are able to interpret, yes, by another coefficient the strength of existing determination, dependency, yes? We can assess the quality of the model using the coefficient of determination R squared, yes? With Mr. Hellman, you talked about R squared. R squared is written here in regression analysis. We need to know regression sum of squares and total sum of squares, yes? And this is the same like we calculated during Anova method. As you can see, SS sum of squares, total sum of squares, regression sum of squares, and error sum of squares. For our calculation, we need regression and total sum of squares. So we will do this, yes? We need to fit the data, yes? I must fit all data set. So I will delete this part, yes? I will delete this part. And we must fit the data, yes? Y estimate. How can we fit the data? 1.331 plus 3.714 times 1. 1.331 plus 3.714 times 2. 1.331 plus 3.714 times 3. 1.331 plus 3.714 times 4. 1.331 plus 3.714 times 5, etc., etc., etc. I don't need these means anymore. So I will delete these means. There will be 1.331 plus 3.714 times 6. Okay, I will delete this. Okay, and we will fit the data, yes? I will fit all data set. 1.331 plus 3.714 times 1. 5.05, I will use only two decimals, yes? 5.05. 1.331 plus 3.714 times 2. 8.76. 1.331 plus 3.714 times 3. 12.47. 1.331 plus 3.714 times 4. 16.19. 1.331 plus 3.714 times 5. 19.9. And 1.331 plus 3.714 times 6. 23.62. Okay. I will delete correlation coefficient because now we will continue with sum of squares. Regression sum of squares. Fitted values minus the mean from variable y, and this must be in squares, yes? Do you remember the mean for variable y? There was written 14.33, am I right? 14.33, y mean, yes? So here I will calculate these differences. 5.05 minus 14.33 squared. 8.76 minus 14.33 squared. 12.47 minus 14.33 squared. 16.19 minus 14.33 squared. 19.9 minus 14.33 squared. 23.62 minus 14.33 squared. Okay, 6 partial results, yes, and the summation will be regression sum of squares. 5.05 minus 14.33 squared. 86.12. 86.12. 8.76 minus 14.33 squared. 31.02. 12.47 minus 14.33 squared. 3.46. 3.46. 16.19 minus 14.33 squared. 3.46. 19.9 minus 14.33 squared. 31.02 and 23.62 minus 14.33 squared. 86.3. 86.3. Okay, the sum will be sum of squares regression. Regression sum of squares. 86.12 plus 31.02 plus 3.46 plus 3.46 plus 31.02 plus 86.3. 241.38. Okay, according to your formulas, this is regression sum of squares, so this is nominator of R squared, index of determination. And now we must calculate the total sum of squares. So we will do this, yes, total sum of squares. We don't need this anymore. And according to your formulas, we need a variable ye, we need the mean, and this must be in squares. So, empirical data, yes, empirical data, this column, this variable y. Okay, in previous case, in case of regression sum of squares, we used fitted data, fitted values, estimated values by our model. Now we are using observed data. Yes. So 6 minus 14.33 squared. 8 minus 14.33 squared. 12 minus 14.33 squared. 15 minus 14.33 squared. 22 minus 14.33 squared. And 23 minus 14.33 squared. Okay. Okay, so 6 squared differences. 6 minus 14.33 squared. 69. 69.39. We can continue. 8 minus 14.33 squared. 40.07. 40.07. 12 minus 14.33 squared. 5.43. 5.43. 15 minus 14.33 squared. 0.45. 0.45. 22 minus 14.33 squared. 58.83. 58.83. And 23 minus 14.33 squared is 75. 75.17. Okay, so the sum of these 6 values will be total sum of squares. 69.39 plus 40.07 plus 5.43 plus 0.45 plus 58.83 plus 78.17. 249.34. Okay, I think that today we had a lot of calculations, so I think that this is enough. We will calculate this ratio and this will be end. So R squared, index of determination, regression sum of squares, 241.38 divided by 249.34. Okay. 241.38 divided by this value, the result is 0.968. 968. So this is R squared. This is index of determination, coefficient of determination. Yes, we know that this coefficient is element of range from 0 to 1, yes. If this coefficient is close to 1, yes, there is more variability explained by our model, yes. More variability inside this data set, yes, explained by our model. So this difference, this small difference between 15,000 and 16,000 Norwegian crowns, yes, this is not a problem, yes, our model is good model, quality model, explaining enough of variability, yes, because R squared is close to 1. Okay, so this is the last example. We will solve example 4.5 later in the next seminar. We will try to use Microsoft Excel solver for estimation of parameters of regression line. You can see that we have here a lot of decimals, and it will spend a lot of time, yes, for calculation manually. So next week, more examples in Excel. I will show to you also the charts, yes, the scatter plots with values and with regression line, and we will continue according to situation. So that's all for today. I hope that you don't have a question, and I hope that I will see you next week. Next week, the 5th seminar, probably in the same way, in this digital form. So have a nice day, and bye.